In previous videos, we introduced the sample analog principle, and many estimators are motivated by this principle. Some of the estimators that we introduced that are motivated by the sample analog principle have the good property of being unbiased, and some others do not have this property. So just to list the examples that are unbiased that we have talked about. So the unbiased estimators include the sample average, as an estimator of the population expectation, it is unbiased. And the sample variance estimator with that adjustment is also unbiased for the population variance. These estimators are unbiased. Well, we also introduced some estimators motivated by the sample analog principle, which are not unbiased, which are biased. For example, Sx, which is the square root of Sx squared, it is a sample analog estimator for the standard deviation of x. It's a pretty reasonable estimator for the standard deviation of x, but it is not unbiased. The reason that it is not unbiased is because expected value of Sx squared equals the variance of x. Expected value of Sx equals the expected value of the square root of Sx squared. Because square root is not a linear function, expectation cannot enter the square root. Therefore, expectation of the square root is not equal to the square root of the expectation. Square root of the expectation of Xx squared is the standard deviation of x. So Sx is not an unbiased estimator of standard deviation of x. In the other estimators that we introduced, which are biased as well, for example, the variance-based estimator for lambda, one of the variance-based estimator for lambda, in the zero frequency-based estimator for lambda, it is also not unbiased. So that estimator is minus natural logarithm of the sample average of the frequency of zeros. And that estimator is not unbiased because of this nonlinear function, that is the minus logarithm function. The estimator that we proposed for the dispersion of transmission rate of a disease, K, so the K value, is also not unbiased. So that estimator is xn bar squared divided by Sx squared minus xn bar. This estimator is quite reasonable because we are using xn bar to replace expected value of x. Xn bar is a good estimator, unbiased estimator of Ex. And Xx squared is a good estimator for variance of x. We plug in these good estimators for these quantities to obtain an estimator for K, but the K hat is not an unbiased estimator for K because K is a nonlinear function of these quantities. So all these estimators are very reasonable estimators, but they are not unbiased. Are these unbiased estimators still any good? Can we still justify using these estimators even though they are not unbiased? The answer, fortunately, is yes. I say fortunately because for many parameters, there is no unbiased estimators. So fortunately, if all estimators that are biased are garbage, then we will be in a very difficult situation. Then we will not be able to estimate a lot of the parameters for which unbiased estimators do not exist. So fortunately, the answer is yes. These biased estimators can still be good estimators in some other sense. In particular, they can still be consistent. So what is consistency? So that the definition of consistency is as follows. An estimator theta n hat of theta is consistent if the sequence of the estimator, when you consider n going from 1 to infinity, or just going to infinity from anywhere. So you consider the sequence of the estimator as n go to infinity. If that sequence converges in probability to theta, then theta n hat is a consistent estimator of theta. So what you want is for the estimator to converge in probability to theta. So what is convergence in probability? I'll define the concept first and then explain what it means. So what is convergence in probability? Convergence in probability means for any positive number epsilon, the probability that this sequence of estimators is more than epsilon away from theta, from the true value it's estimating, converges to 0. So if the probability that the estimator is more than epsilon away from the true value converges to 0 as n goes to infinity, then we say theta n hat converges in probability to theta. So convergence in probability is a variation of the convergence concept that we learned in calculus. Now, why do we need this extra concept? Why is the convergence, the calculus convergence, not enough? The reason that we need this concept is that the sequence we're considering is random. So each estimator theta n is a random variable. Because it is random, its realization, the realization of the sequence depends on the state of the world, depend on the realization of the state of the world. And usually, it is not possible to guarantee that in all states of the world, theta n hat will converge in the calculus sense to the true value theta. Okay, so that is why we need a weaker concept than that convergence than that calculus convergence. And this weaker concept is convergence in probability. To explain that in a more concrete example, let's consider the coin toss example that we talked about before. So in that example, we define this x variable. So this x variable is a dummy variable that equals 1 if in the coin toss, the coin land heads up, and 0 if tail up. And the parameter p, so x follows a Bernoulli p distribution with the success rate p. The parameter p equals the probability of success of head, probability that x equals 1. Now, to estimate this p, you can toss the coin many times, say n times, and use the sample average of xi to estimate P. So P hat is the sample average of Xi. This P hat, intuitively, when you toss the coin many times, like thousands or millions of times, the sample frequency of observing head will be very close to the probability that X equals 1. So if the coin is fair, this would be a half. So if this is a fair coin, then when you toss the coin many times, like tens of thousands of times or millions of times, the sample frequency of observing head will be a half, will be close to a half, very close to a half. However, that is very intuitive. However, no matter how large n is, no matter how many times you toss the coin, no matter how large n is, the probability that you get a full sequence of head for example, that probability is p to the power n is positive. The key is that this probability is positive no matter how large n is. And when in this state of the world, in the state of the world that all of the coin tosses turn out to be 1, p hat equals 1. So the probability that p hat equals 1 is positive always, no matter how large n is. So the probability that p hat minus so what that imply is that it's not possible to guarantee that p hat is close to p, because 1 is not close to p. No matter how many times you toss the coin, it's not possible to 100% guarantee p hat will be close to p. So the best we can do is instead to say that the best we can do is to guarantee that p hat is close to p with high probability. Okay, is to make sure that p hat is close to p with high probability. And the concept of convergence in probability does exactly that. So if p hat converges in probability to p, which is also denoted by p hat arrow sub p, if p hat converges in probability to p, then for any given interval, for any given interval around theta, any given interval around theta, so theta minus epsilon to theta plus epsilon, so this is an interval around theta. No matter how small epsilon is, the probability that p hat will belong to this interval. So here the p is actually, theta is actually p. So let me write p. Theta belongs to this interval will converge to 1. So this convergence is the standard calculus convergence, because this sequence is a probability, it's non-random. So this is a non-random sequence, so this convergence can be the standard calculus convergence. So p hat converges, converging in probability to p means that the probability that p hat is close to p, judged by this epsilon tolerance, gets larger and larger. It approaches 1. Okay, so that's what convergence in probability means. So for large n, p hat can still be very different from p, but the probability that happens will be very, very small. And the probability that happens will go to 0 as n goes to infinity. So that's what convergence in probability means. So an important tool to prove consistency of estimators is the law of large numbers, or in short, LLN. So the law of large numbers. This is the statement of the law of large numbers. So it says, if xi, I runs from 1 to infinity, is an IID sequence drawn from distribution F, and if the variance of x is less than infinity for random variable x following the distribution F, so the variance implied by the distribution F is less than infinity, is finite. If these two conditions are satisfied, and then the sample average, where the sample is the first n element of this IID sequence, then the sample average converges in probability to the population expectation. So this is the statement of the law of large numbers. So this is one version of the law of large numbers. There are other versions, but this version is the simplest to argue for. Okay, so you need two conditions. One is that you got an IID sequence. Your sample is IID. And the other is that the population variance is finite. So you might be wondering why do we consider an IID sequence, even though in estimation we're just using n observations? Why do we use an infinite sequence? The reason is, for law of large number or for consistency, we have to go through this thought experiment of increasing sample size. Our statement is about what happens when we increase the sample size to very, very large, to infinity. So in this thought experiment, we need to make a commitment of what we want the data to be like when we increase the sample size. So even though in practice you only have the sample size that's n, that's either 100 or 200 or 300, whatever you have with your data set, in practice we only have that finite n. But consistency, or law of large number, is a thought experiment where you imagine what happens when you increase the sample size, when you collect more sample. In this thought experiment, we require that when you add more sample, you're adding the sample in an IID way. So that's why we consider this infinite sequence. All right, so that's the statement of the law of large numbers. This version of the law of large number is rather easy to prove. I'm going to go over this simple proof. So the proof is as follows. We're going to use the definition of the convergence in probability. we're going to consider this arbitrary small positive number epsilon. So this is an arbitrary small positive number epsilon. For this positive number, we consider this dummy variable defined by the event that xn bar is more than epsilon away from the population expectation. So this dummy variable equals 1 if this event happens and equals 0 otherwise. Okay, so if you write out the definition of this dummy variable, it takes two values. It takes the value 1 if this condition happens, or that condition can be written equivalently as this inequality. So all we have done is to divide both sides of this inequality by epsilon. So this dummy variable equals 1 if this ratio is greater than 1 and equals 0 otherwise. Now, if you look at this formula, you find that there are two cases, right? But in both cases, you have the following inequality hold. In the first case, 1 is less than this ratio because this dummy variable only equals 1 if this ratio is greater than 1. So it is less than that ratio. That's in the first case, this dummy variable is less than this ratio. In the second case, the dummy variable equals 0. It is also less than or equal to this ratio because that ratio is always non-negative because due to this absolute value sign. So in the second case, this dummy variable is also less than or equal to this ratio. So in both cases, we have the same upper bound. That means this upper bound, you actually don't have to write the two cases because they are the same in both cases. So that equals this ratio of xn bar minus ex and epsilon. So what have we done? We have found an upper bound in terms of xn bar minus ex divided by epsilon, absolute value, for this dummy variable. So this dummy variable is less than or equal to this random variable in any state of the world. So in any state of the world, this random variable is less than or equal to this random variable. And therefore, expected value of this random variable has to be less than or equal to expected value of that random variable. And moreover, expected value of the square of this random variable has to be less than or equal to the square, expected value of the square of this random variable. So we have expected value of this dummy variable squared so the square of this dummy variable, which actually equals the dummy variable itself, but let's now just write the square of the dummy variable, is less than or equal to the expected value of the square of this. Xn bar minus ex squared divided by epsilon squared. The left-hand side, because we are squaring an a dummy variable that can only take value 1 or 0. So 0 square equals 0, 1 square is 1. So that square is the dummy variable itself. So that's the expected value of the dummy variable itself. And that is less than or equal to. So this expectation, so epsilon square is a constant. So that can be factored out of the expectation. And what's left is expected value of x and bar minus ex. But ex is also the expectation of x and bar because x and bar is an unbiased estimator of ex. We have done that calculation before. So therefore, this is expected value of the square of the deviation of x and bar from its own expectation. Well, that is the definition of variance. So that is the variance of x and bar. Now, if you look at the left-hand side, that's expected value of the dummy variable. Dummy variable follows the Bernoulli distribution with success rate equal to the probability that this event happens. And expected value of the Bernoulli random variable equals the success rate. So the expected value of the dummy variable equals the probability that the event defining the dummy variable happens. So equals probability that this event happens. And on the right-hand side, 1 over epsilon squared doesn't change. But for the variance of x and bar, we have done this calculation before. The variance of the sample average in the context of IID sample equals the variance of x divided by n. So x is a generic random variable following the population distribution. All right, so we got this bound. And now if you look at the right-hand side, variance of x is a finite constant. It doesn't change with n. It's a finite constant. 1 over epsilon squared is also a finite constant. So on the right-hand side, it's actually a finite constant divided by n. What happens to that when n goes to infinity? This converges to 0 when n goes to infinity. Therefore, the limit of probability that x and bar is different from x differs from ex, sorry, the probability that x and bar differs from ex more than epsilon is less than or equal to the limit of variance of x divided by epsilon squared divided by n, which is 0, because n is on the denominator. As n goes to infinity, this ratio goes to 0. And clearly the probability cannot be negative, so this is greater than 0. The limit is therefore also greater than 0. If it is greater than 0 and, it's greater than or equal to 0, probability cannot be negative, so this is greater than or equal to 0. Therefore, the limit is also greater than or equal to 0. It is greater than or equal to 0 and less than or equal to 0. So it's bounded from up, above, and below by 0, so it has to be 0. So that has to be 0. That proves the law of large numbers. All right. So that is a simple proof of the simplest kind of law of large numbers. And I want to point it out that this formula, I didn't give it a name. We derived this formula, but this formula actually is called the Chebyshev inequality. Chebyshev's inequality. So you can appeal to the Chebyshev's inequality and directly write down this statement. But we didn't do that. We derived this statement from the very basics. So which is not hard, as you can see. So you can derive this inequality from the very basics without appealing to the Chebyshev's inequality. But you could just appeal to the Chebyshev's inequality. All right, so that's the law of large number. Let's consider some applications of the law of large number. In order to apply the law of large number to prove consistency of various estimators, we're gonna need a different theorem, a different result. That's called the Slutsky's theorem. The Slutsky's theorem is as follows. Suppose you have random sequences y1n and y2n. Both sequences converge in probability, one to a point C1, the other to a point C2. C2 and C1 are both non-random scalar numbers. You have these two random sequences, both converge in probability, and you have also a function g that is continuous at the point C1, C2. That's the limit of the random sequence. Then the transformation of these two random variables, so g of y1n and y2n, converges in probability to g of C1, C2. So what that means is convergence in probability is preserved by continuous transformation. So in words, it means convergence in probability is preserved by continuous transformation or continuous functions. So convergence in probability is preserved by continuous transformation. This is different from unbiasedness, right? Unbiasedness is not preserved by just continuous transformation. Unbiasedness is only preserved by linear transformation. Convergence in probability is much more robust. And that means we can apply this concept to many more estimators. So for example, again, consider an IID sample of X following the population distribution F. The sample average converges to the population expectation in probability by the law of large numbers. So we can also assume that variance of X is finite. So we can appeal to our law of large numbers. So there are more general law of large numbers that are more difficult to prove that give you this conclusion without the finite second moment. But that's for now, just use the one with the requirement for the finite second moment. Okay, so the sample average converges to population expectation. This intuitively should be true according to the frequency point of view of probability. And rigorously, it's also true. Mathematically, we can prove it using the law of large numbers. So by law of large number, this is true. And Sx squared equals 1 over n minus 1 times summation xi minus xn bar squared. For this one, we cannot apply the law of large number directly because this is not an IID sequence. Why not? Because xn bar appears in every eye, in the observation for every eye, and that creates dependence across eye. So you can treat this as a random variable, as an observation, but that observation is not IID across I because of the common element xn bar. So you cannot apply LLN directly. You're going to have to work on this formula to obtain quantities that you can apply LLN on. So the way to do that is to write out the square. Once you write out the square, you find that equals 1 over n minus 1 sum of xi squared plus n over n minus 1 xn bar squared minus 2 times 1 over n minus 1 sum of xi times xn bar. And that equals, so for the first term, that is n over n minus 1 times 1 over n sum of xi squared. So that is n over n minus 1 times the sample average of xi squared plus n over n minus 1 xn bar squared minus, if you look at this term, you see xn bar doesn't vary with I, so xn bar can be taken out of the summation. So what you are left with is 2 times xn bar times 1 over n minus 1 times n times 1 over n summation xi. And this is xn bar, right? So you can erase that and join that xn bar with this xn bar. So that becomes xn bar squared times n over n minus 1. So now we can appeal to the law of large number and the Slutsky's theorem. So by law of large number, this quantity converges to expected value of xi squared. So now you're viewing xi squared as a random variable. And you have an IID sample that's xi squared, I runs from 1 to n, of x squared. So that converges in probability to expected value of x squared. You can also write xi squared because xi follows a distribution f as well. Just for simplicity, I'll just write ex squared. Okay, so by law of large number, that happens. And also by law of large number, xn bar also xn bar converges in probability to E of x. Actually, you may want to simplify these two terms first. For these two terms, as you can see, it's n times n minus 1, which can be factored out. x n bar squared minus 2x n bar squared. So it's just a minus x n bar squared. So after simplification, it becomes this. So this sample average converges to expected value of x squared, and this converges to ex squared. N over n minus 1 converges to 1. Therefore, this whole thing converges in probability to e of x squared minus square of ex, which recall is another form for variance of x. So this adjusted estimator for the population variance is consistent for the population variance. And sx squared equals square root of x sx squared. Sx equals square root of sx squared. And the square root function is continuous. Therefore, by the Slutsky's theorem, that equals the square root that converges in probability to the square root of the probability limit of sx squared, which is variance of x. And that equals the standard deviation of x. So little sx is a consistent estimator for the standard deviation of x. Similarly, you can show that k hat also converges in probability to k by the Slutsky's theorem. So these are all by the Slutsky's theorem. You can also show that this unadjusted variance estimator, which is 1 over n sum of xi minus xn bar squared, that is also consistent for variance of x. That you can show that by going through the same arguments, or you can just realize that this is, or you can just realize this is a function of x sx squared. So this is n minus 1 times over n sx squared. And because sx squared converges to variance of x, and n minus 1 divided by n converges to 1, so therefore that also converges to the variance of x in probability. So it seems that all the estimators that we introduced, based on the sample analog principle turn out to be consistent, even though many of them are not unbiased. So consistent estimators, so they are still good estimators in this sense. Consistent estimators are close to the true value with high probability when the sample size is large.